Now we get to finish up our linear models lecture. We're going to do this through the lens of a really interesting classifier called the support vector machine. It's an unintuitive name, but let's get to it. Let's pretend we're the Singapore Land Transport Authority, and we need to build a new highway to help shuttle different goods and people between different parts of the island. We're going to do that by making a new east-west highway, but we have to pay attention to not destroy all of the environment. For example, we might have some heritage trees, which are old trees that we want to preserve. So in this case, in this diagram, we've plotted 4 heritage trees, 2 of which are red, which we've decided to keep on the north side of the highway, and 2 that are blue that we've decided to keep on the south side of the highway. And like good highways that help accommodate fast travel speeds, we're going to make the highway as straight as possible. Here, a linear separating hyperplane, right? You see where we're going with this. Okay, so what I want you to do is think about a line that you want to draw on this diagram to show where the highway should go, okay? And I want you to pause the video and draw a line for me, okay? All right, so you paused the video and hopefully you did this exercise. Hopefully you drew a line a little bit like this one, okay? Something that runs from southwest to northeast. And this is a great line because actually it separates the red heritage trees from the blue ones just fine. But it's not the only line you could have drawn, right? There are many others. You might have drawn like this line or this line. They also work quite well in separating the north trees from the south trees. But I think most of us would say, they don't look particularly good. Why is that? Why would we not want to do that? So one thing that might strike you is that the red line is somehow a better line. How can we characterize this? Well, if we're going to build a highway, well, we need enough lanes to move things to the left and the right. And if we were to think of lanes on the red highway, we could make a fatter line, right? So we could draw a line like this and like this to allow traffic to move on both sides of the divider of that highway. If we were to choose one of the blue lines to build our highway, we wouldn't be able to make such wide lanes, right? So you can see here, we can barely eke out a line that's going to give us a little bit of leeway, maybe just for one lane of cars and vehicles to move on either side. And that would be true for the other blue line as well. So what's the problem here? If we want to define a good hyperplane, somehow we want to put it smack in the middle between the positive and negative points, such that we can have a wide margin of error between both sides. So what do we mean by that? We want to define a better linear separator. And we've got 2 questions for ourselves. Why would we think such a bigger margin is actually a good thing for us, right? So you can see as we go from the left side of this diagram to the right side, we get successively larger margins until on the right side, we basically can't squeeze any more margin out of the diagram. It's going to hit both trees on the north side and a tree on the south side. It's going to be the fattest margin, fattest highway we can draw. Okay, and if we agree that in fact large margins are better, then why or how are we going to be able to optimize our theta, our parameters, such that the linear classifier can achieve this maximal marginal output? And here's the answer to the first question. In fact, it's sort of intuitive. If we start with the diagram on the left side, right? And we think about each of these points being measured. If we measure that point just a little bit off, okay? For example, this point, instead of measuring here, we measured it over here. It would still be okay. But take a look at the red point, the red heritage tree on the bottom. Let's say our surveyor didn't quite make the right observation, and actually that tree is somewhere over here. Uh-oh, when we planned our highway, we put the divider down. Now that tree is going to be misclassified as a blue tree. That's no good for linear separation. Okay? So the idea between a wider margin and noisy data is very apparent, right? If we have noise in our data, we can handle more data noise by using a larger separating hyperplane with a larger margin, right? As we go to this case over here, even if we had misclassified the same points, we would still be safe because our highway was drawn with a larger margin to cater for cars on the left and the right of the highway. So unfortunately, or fortunately if you want to be examined on less material, we don't have the capability to, in this series of lectures, to go over the details of a SVM proof, of how to derive it. But I'm going to give you the outline and the intuition, because I think that's the nifty part of SVM that I'd like you to retain. We're going to basically try to look at a way of defining where the hyperplane is by guaranteeing that all points that are blue and all points that are red are at least some distance away from the separating hyperplane. We're going to do that by defining the closest points to the hyperplane as having a unit distance. That means a distance of 1. Okay? It doesn't actually matter what this value is, but when we fix it, it's going to help us narrow down to a unique solution, which is invariant of scaling. Okay? We're going to set up a set of inequality constraints using constraint optimization to solve this problem. It's going to turn out to be a quadratic programming problem that you might be able to learn through optimization theory in other courses at NUS. And we're going to see that by just looking at only a very small portion of the data set, that is, the points that are nearest to the hyperplane, which we're going to call support vectors, okay, these points here, okay, those are going to be the points that uniquely define our hyperplane. So just like the perceptron learning algorithm, we can discard all of the correct points except for the ones that it clearly define where the hyperplane goes. Okay, so this means the support vectors, or those data instances that are close to the hyperplane, are the ones that entirely define the classification hyperplane. And as you'll see from the previous part of the lecture, that means the model complexity is basically just catered on how many support vectors there are. The smaller the number of support vectors that define the classification hyperplane, the less complex the model is, and as we saw, the more general the solution will become. So typically when you look at a support vector machine picture in a machine learning book, you don't see it with this nice linear separation. You see it with this type of squiggly line as we've shown you on the right. And this is because support vector machines are really cool. They can support nonlinear mapping very natively. The idea is through this concept of what's called a kernel. Not the kernels that we have in collab notebooks or things of this sort, okay? A kernel is basically a kernel function. And a kernel function is basically one that calculates the similarity between 2 points in space, okay? So we can use that to calculate a distance value for 2 points, or a distance value between a point and a linear separating hyperplane. And we can do this in a nonlinear way, so that we take the X space and expand it into a nonlinear space, perhaps even of infinite dimensions, and we will be guaranteed to find a classification hyperplane that allows us to separate even any most gnarly type of space in the original space. When the support vectors live in Z space, when we see them in the original X space, we call these pre-images of support vectors. You can see some of them here. The ones with the slightly darker circle around them, these are the support vectors that when we blow it into high dimensional Z space, they're actually sitting nice and pretty as the support vectors on a linear hyperplane. So the margin is then again, maintained only in the Z space and not in the X space. And this means, again, great things because we can handle a nonlinear boundary, even in the case of using very little data. Again, just the number of support vectors characterize the complexity of this particular linear classification solution.